Hey guys, welcome to Code Decode. In this video, we are going to look into microservices scenario-based questions that eliminates most of the candidates from interviews. The very first and a very common problem in a microservice-based scenario questions is a duplicate problem. When two payments arrives at the same time, how would you prevent the double payment across microservices? So suppose you have an e-commerce system, there's an order service, there's a payment service. You place an order, but your payment's still pending. You either click on refresh or go to back and then again do the payment. That means you have paid twice. You do the payment procedure twice. So when two payment requests arrive simultaneously, basically we should never rely on application level locking. In microservice architecture, you can have multiple pods for payment service, and there might be a case that if two payments are coming, they might go to different pods, and you will end up having two different payments for the same order from the same customer. So you are charging double for one order. So the key idea is, if the same payment request is coming twice, it should always represent the same result. Basically, it should not reproduce two payment IDs but have the same effect, that is, take payment only once. Let's assume an architecture. There is client, there is an API gateway, there is an basically this is an e-commerce system. Okay, so there is an API gateway where the request comes, there is a payment service, there is a payment gateway. What is a payment gateway? Like UPI gateway, net banking, debit card. Now, if customer clicks on pay now twice, both requests are arriving at the same time. Suppose there are two pods. Now request 1 comes, it checks the payment status is pending and status is not paid. Then request 1 also charges the customer, request 2 also charges the customer, and request 1 updates the DB and request 2 also updates the DB. So now you see, for both the request we have charged the consumer, and hence he has paid twice rather than once. So this is a race condition. And why synchronization is not enough? Many people will say that since there's a race problem that both are charging twice for the same status, I could do synchronization. But synchronization works in a monolith application. In a microservice application, payment service has multiple instances. Request might hit different pods. Each JVM has its own memory, and synchronization works only with one JVM. So two JVMs having two different pods, same request coming for two pods, there will be no synchronization working in different pods. Therefore, synchronization is not enough in a microservice application where you might have more than one pod. Therefore, it will not prevent duplicate payment across instances, and the better option is to use idempotency. What is idempotency? That is, an operation is called as idempotent that if executing the same request multiple times result in same result. That means if the first request is charging the customer, the second request will say that whatever is the result of the first payment is going to be shown by the second request. This is idempotency. It is not going to create one more payment row in the payment table, and it is not going to call the payment gateway service again if payment gateway service was already called with the first request. So what you can have done is, in the order service, while calling for the payment microservice, you could have created the key called as payment ID. Say pay for order 123. So there is an order which is ID with the ID 123. Now you were creating the payment for that order. So you create the key with the order ID. So now for one order ID, you can only take one payment. And that payment ID with the order ID in the key makes sure that only one payment is taken for one order. So now both the request contains the same key. The payment service stores the key in the database, and when with the unique constraint on the key, it makes sure that the second does not take the payment again or do not create any other row for the payment. So how the request would flow? The request 1 receives the payment request for order ID 123. It inserts the payment row in database with the key as pay order 123. Now the key has the unique ID as 123. Now it charges the consumer and marks the payment as success. At the same time, the second request comes with a different pod. It is trying to insert into the same table with the same key pay order 123, but the database has unique constraint. So it is unique created on the payment key with the idempotency key. So the unique constraint fails, it cannot create another payment, it will not call the payment gateway, and payment will not be charged. Rather than that, it is going to fetch the existing row which was already saved and return the whatever success, failure, pending, whatever status it is going to return the same one. So that is how, even if you create the third or fourth request, since the key is same, it is not going to insert anything into the database, rather it is going to return whatever the existing row sends you the data. So customer is charged only once, and every time it tries to pay again and again, it says this order is already either succeeded or failed, or it is in progress, wait for some time. So what will be your payment service algorithm? As soon as the payment request is received, to take the payment, do not call the payment gateway. First create and extract the idempotent key and try inserting that in the table with the pending status. If there is no key, then your insert will be succeeded. You call to the payment gateway, take the payment from him and update the status as success. Otherwise, if you try to insert the key but the status is either already success or failure or pending and duplicate key error comes, then fetch the existing payment and return the previous result. This pattern is used in many payment services to prevent the duplicate payment systems. And this is one of the very important microservice interview trap with scenario based question, which you should know. So how would you create a transactional Spring Boot approach? Onto the process payment, you make transactional. In the payment repository, you save a new payment with pending status. You charge and you set the status as success. And then next time you try to save it, if that key is already present, then do not do anything, just return whatever it is there already in the first row of the database. So now if another request tries to insert, database throws duplicate key exception, you catch it and return the existing payment. But there is one scenario. Suppose there is a row which is inserted as pending, that is processing, but your server crashes. Now customer may have been charged, may not have been charged. So if duplicate request is received, you are still in pending status, but it is not going to call any API gateway because it has crashed. So you will keep on returning the payment processing and do not poll gateway or resume processing until you know whether it is success or failed. So the best approach in this scenario, that if the first request comes, it marks your row as pending payment and it crashes even before taking the payment from the consumer. Now consumer keeps on waiting because it thinks that it is going to call the payment gateway and take the payment from him, but it is not doing it. So the best approach to prevent the crashes and hanging state of your order in payment pending status is that you create a recovery job which runs at a scheduled time, say every 30 seconds. Find all the payments which are in pending status. Call the payment gateway and check whether the payment is really taken or not. If it is already taken, mark it as success. If it is not taken, mark it as failed. But do not keep the status as pending for more than 30 seconds. And then you update the database that, okay, the payment is succeeded or payment has failed. But keep a job already running, which is scheduled at every 30 seconds, which searches all the orders whose status are still payment pending and mark them into the terminal state, whether it is successful or failed based on the current scenario, asking the current logs from the payment gateway. So this is how you solve the duplicate payment problem. The second very most important problem that comes in a microservices, that your order is created, but your payment has failed. Now what will happen? Your inventory was already reserved. How would you maintain the consistency? How would you deallocate the inventory so that other people can take it? Take an example. There is a sale going on in Amazon. You purchase 10 phones from there. Only 10 phones were there in sale. You take all 10 of them in your cart, but your payment is not going through. You do not have enough money. Now inventory is already reserved. So the phones which can easily be sold at a good amount to the proper consumer is of no use because it is reserved by one of the consumer or customer who cannot pay for it. In this situation, you have a business loss. So you have to roll back your inventory and your order should be in the cancelled state if the payment is failed. Many of the people come and say, I'll just use at the rate transactional and make the order service, payment service, and inventory service a part of one transaction. That is a very big mistake, because in microservice there is nothing called as one transaction. Your services itself are distributed, so your transactions are also distributed. You can create a transactional thread only in the monolithic applications. In microservices, there is nothing called as ACID. It's all eventual consistency. So, for example, assume a scenario: you have order service, payment service, inventory service. Now, you create an order, you reserve the 10 mobiles which are on sale in the Amazon Big Billion Day or something, and then you try to pay for it, but your credit card does not have enough money for it. So, your payment fails. Now, for all the other users who are trying to purchase that phones in such a low price, they are all waiting and they are not able to purchase those phones even though they are available, because your inventory is already reserved for the consumer who cannot pay for it. So currently order is created, inventory is reserved, but your payment has failed. This is an inconsistent state, because consumer was not charged, but my inventory is not sold to any other consumer also, or it's not even visible to others because it is reserved for the person whose payment has failed. If you do nothing, your stock becomes unavailable, the other consumer cannot buy it, and your inventory leaks over time. Why at the rate transactional will not work? Because that works only with one database. But in microservices, order service will have its own order database, payment service will have its own payment DB, inventory service will have its own inventory database. So each service has an independent transaction. You cannot do the asset property kind of stuff in these different databases because your databases are different. So if your payment fails, you cannot automatically roll back your reserved inventory and you cannot roll back your order. The best way to fix this is Saga design pattern. Yes, the Saga, exactly the one which is of two type: orchestrator or choreography design pattern. So a Saga is a sequence of local transactions. If one step fails, the previous completed steps are compensated. So in a Saga design pattern, a very important concept for rollback is compensation and not a rollback. Because a business rollback is not possible when databases are different. You only and only can do a compensation for what you have done wrongly, because your transaction is not completed successfully. So step by step flow is: you create an order, your order is in pending state. Now order created event is published onto either Kafka or through an orchestrator. Now it reserves the inventory, it reserves one laptop. Now it tries to process the payment, calls the payment gateway, payment fails, it publishes the event called as payment fails. Now your system goes into a compensation state. A compensation state is where the inventory service receives the event that payment has failed. So it has to reserve and release the reserve that is created, and now after the release of the inventory, the reserved is 0, and now that laptop is available for other consumer. And then it says inventory is released, so now your order service says it is going to convert the order status to cancelled. So now the final state will be: order is cancelled, inventory is released, and payment is failed. And now the system is consistent again after all these compensation events are successfully processed by each and every microservice. So for a visual sequences in a Saga design pattern, order is order created, inventory is inventory reserved, payment has payment failed. Then a compensation starts in these three microservices, where inventory goes into compensating event, where inventory will be released and order will go into cancel status. Now you have two options to implement Saga: the choreography and the orchestrator design pattern. The choreography is a simpler one, where all of these communicates through events: order created event, inventory reserved event, payment failed event, inventory released event, and order cancelled event. Now each service react independently. The pros is they are loosely coupled and scalable, but it is only and only for the small microservice architecture. It is difficult to trace like who is using which particular event is consumed by which microservice. It is very difficult to trace and it is very complex to debug. The second option is orchestrator design pattern, which is a central Saga orchestrator, where orchestrator create the order, Orchestrator orchestrate the inventory reserve and try to process the payment, and if payment fails, it is the task of orchestrator to release the event, and it is a task of orchestrator to mark the order as cancelled. The good part is it is easy monitored, easily retried, and centralized control. The con is it becomes the critical component and becomes the single point of failure. Now, a second question can be asked when you explain them the Saga design pattern for a situation where your order is created, inventory is reserved, but your payment fails. Then they might ask you that what if your compensating event fails? For example, your payment has failed. Now you say, okay, I want to become consistent. So I'll create an event called as release the inventory. Now, a interviewer might trick you with the fact that what if your release inventory fails? Suppose your payment is failed, that is fine, but your release inventory also failed. Now your compensation itself is failed. What will you do? The best way is to fix it using either retry compensation or use a durable messaging, ask them to compensate whenever the system is up. It will use Kafka and fix it. You can use dead letter queue for repeated failures. You can keep Saga in compensating mode so that if it isn't compensating, it will just keep on trying and trying until the compensation is done. Or you can manually intervene if nothing of these work. Never assume the compensation will always succeed. So, in a situation where order is created, inventory is reserved, but the payment has failed, I will try to implement the Saga design pattern, which is the best for the distributed transaction systems. So, if the payment fails, payment service publishes a payment failed event, inventory service compensates by releasing the reserved stocks. Order service updates the order to cancelled. This maintains the eventual consistency across microservices. But I will not stop at making sure that a compensation actually happens, because any transaction can fail at any point of time in a distributed system. So I would try to make the compensation idempotent with durable messaging retries, dead letter queues for even the failure recovery in the compensating events also. Now, third, service A times out. For example, your order service is calling the payment service synchronously. Remember and very emphasize on the word synchronously. And then your payment service becomes slow. So will you keep your order service keeps on waiting for a n number of times? What happens under load? Does your retry help you? How would you fix it? So these are the scenarios which for sure whenever you have a distributed systems like microservices, these issues will come, and not able to answer, make sure that you are not aware of the distributed systems. So if your order service is calling the payment service synchronously, but by any chance the dependent service becomes slow, then your order service thread start waiting for payment responses. Now under load, when a lot of number of requests comes in, each thread is handling one request, and request is already stuck because payment service is not going to respond you. In such load, the waiting thread accumulates, the thread pool becomes exhausted, retries and all those things stops working, and we will become in a very disastrous situation. And that is where we should use timeouts. That if the payment service is not responding in 5 milliseconds, I will come back and say, sorry, payment service is down. I will stop taking the request. I'll use a circuit breaker pattern. I will keep the circuit open. No request will come to payment service until the payment service is up. And then I'll retry again and again with proper backoffs. And then asynchronously, I'll try to do the introduction of Kafka between the order service and payment service, so that whenever payment service is up and running and healthy, it will take the request from the Kafka, take the payment, process the payment, and then mark the order as completed or failed. So the architecture for this situation will be, there is a client calling order service is calling the REST API call at payment service. Normally it is fine. Now payment service becomes slow. What happens? Now when you would have usually gotten 100 milliseconds, you stopped having the response till 5 seconds. So now order service receives 1000 requests per second. What happens step by step? Request received at order service calls payment service. The thread is waiting for 5 seconds. By the meantime, new thread continues working because a new request has arrived. More thread becomes blocked for more than 5 seconds. Now thread pool becomes full because the threads are getting stuck for 5 seconds for a payment service to respond to. Now, incoming response cannot get a thread, order service starts timing out. This is called thread pool exhaustion. Why this is a cascading failure? Because what happens, your payment service is down, your order becomes slow. The API gateway becomes slow, client tries to retry. If it retries, number of requests increases, traffic increases. And with more number of traffic increases, more number of threads are blocked. And at a time you will come out of thread possibility in a situation of in such situation. So your payment becomes even more slower, everything starts failing, and that is cascading failure. Because if one dependent service is down, all the services that depends upon the payment service also becomes down. Also, what is a thread pool situation here? Suppose order service has 200 threads. Now, if the payment service waits 5 seconds, maximum concurrent waiting requests are only 200 because it has only through 200 requests. Now, as soon as the 201st request comes in the system, it goes to the waiting queue because all the 200 systems and threads are waiting for payment system to respond. Now latency increases, your timeouts occurs, memory usage grows, CPU remains slow because threads are waiting. Now, how would you fix this issue? So we understand the issue. What happens when your order service calls the payment service is slow. First of all, do not keep on waiting for 5-10 seconds. You can easily create the connection timeout and read timeout configurations for the REST template. So if payment succeeded, that's fine. If payment fails and cannot respond in 2 seconds, fail fast. Release the thread. This prevent the thread exhaustions. You can use a circuit breaker pattern. Without circuit breaker pattern, you will keep on giving a call to payment service. And even when payment service is unhealthy, you keep on giving it. But with circuit breaker, you would stop calling the payment temporarily. Return the fallback method and periodically test, is my payment service up and responding quickly, or it is still broken. And circuit breaker states whether it should be closed, open, or half open. Closed will be when it is a normal execution, payment service is responding within 100 milliseconds. Closed is when, open is when it is not responding at all. Half open is when it is trying to test whether payment service is now up or not. The third is retries, but you have to be very careful. This is where most of the candidates go wrong. They would say, I'll blindly retry until the payment service is up. Now, payment service takes 5 seconds, order is retrying 3 times. So, your one request for taking the payment for order ID 123 becomes 15 seconds because each request takes 5 seconds. 5 and now for 3 exponential retries, it will be 5 plus 5 plus 5, 15 seconds. Your traffic tripled, your latency tripled, your payment gets overloaded even further because each request is now divided into 3 more requests because of retries. So retry only when a situation there is a transient failure, not always that is a circuit open. Use exponential back off, add jitters, and add a retry limit. For example, do not retry immediately, wait for some time and then retry. The fourth way to fix this is bulkhead isolation. So you have seen when payment service is not responding and you have only 200 threads, your 201st thread is waiting in the queue because you have exhausted all your threads. Now, if the thread was one for payment service, one for customer service, one for inventory service, you have exhausted all the threads. So bulkhead means separate the thread pools. So you have suppose 200 threads. Give only 50 threads to payment service, 50 to inventory, and 100 to consumers. So that if the payment service is down and slow, it is not responding, your payment failure cannot exhaust all the resources, but your still inventory and customer service keeps on working because threads are still available and not exhausted just because of the payment service. The best fix is asynchronous communication for payment processing. Synchronous communication is usually unnecessary. What you could have done is order service creates an order, it publishes a payment request event in the queue, be it Kafka, RabbitMQ, or ActiveMQ. The payment service processes asynchronously, publishes the payment failed or payment succeeded event, and order immediately returns order received. Benefit is no blocked threads, better scalability, natural retrying, and resiliency. What will happen during a spike? Now, suppose 10,000 request arrives during a spike or a sale situation. In synchronous it will explode because all threads are waiting and latency is like unexpected. It is exploding like anything. But in a asynchronous communication, your request enters Kafka or RabbitMQ topic. The payment processes at controlled state because the producer is going to produce how much consumer can consume. So it is a controlled rate there, and queue absorbs the spike. This is called load leveling. So when there is a very high load or sale going on, you try to do the asynchronous communication. So the main issue is not the timeout itself of the payment service. The issue is the resource exhaustion caused by waiting threads, where order service threads are waiting for payment service to respond. I would fail fast with timeouts, preventing cascading failures with circuit breakers and bulkhead. Use retry selectively with exponential backoff, and for payment processing, I would prefer asynchronous communication so that order service is not blocked because of the payment service being down, which prevents the cascading failures. I have many more questions to cover, like Kafka and other stuff. If you want more such questions, let me know in the comment section.